Hi. Today I will finish the proof of the theorem about uniform convergence on compact sets for CC distances associated to structures that converge. What was left to prove was a lemma, which stated the uniform continuity of the CC distances in terms of some auxiliary Riemannian distance. Okay, let's see the proof, so we conclude. The lemma that we need to prove is the following. Suppose you have compact subsets of real numbers, and you have a manifold, an integer m, and you also fix a value in lambda. Then let f be a bundle map depending on the parameter lambda, and continuously varying norms also depending on lambda. So and together we call this continuously varying CC bundle structure. And we associate the distances so let's call d lambda the distance associated to f lambda and n lambda. Okay. Then we need to assume that the limiting norm, the limiting structure associated to lambda 0 is bracket generating. Okay, so assume f lambda 0 m Rm is bracket generating. And let me also assume some things more to simplify the proof. So also assume for simplicity that let's assume that the limiting distance is complete, or let's assume this boundedly compact. So closed balls are compact. And let's also assume that really like the structure F, the bundle map, it's really a smooth map. I wish to just assume, do the proof in this case, because this is really what we need, right? In the limiting theorem of Pansu and Mitchell, because really the limiting distance is the distance on a Carnot group, and moreover, really the structure also, there's smooth vector fields depending smoothly on the parameter lambda. Okay, so these are the assumptions. The conclusion is the following, that for all compact set in M, compact, and for all Riemannian distance ρ, that we fix, Riemannian distance on M, there exists a compact neighborhood, let's call it I of I0, lambda 0 in space of lambda, and there exist alpha and beta homeomorphisms of the space 0 infinity, so in 0 are 0, such that you have a uniform bound on the distance of points P and Q in terms of this beta and the distance, the Riemannian distance PQ. And this is for all lambda in I and for all P and Q in K. Okay. So this is what we need to prove. Now, actually, we don't really need this bound in the proof of the limiting theorem. So actually, the theorem we proved in the previous video was the fact that this distance d lambda converge on compact set to the distance d lambda 0. They converge uniformly on compact sets. However, this bound was not really needed in the proof. Actually, really, this bound is enough. So this bound is enough for the theorem. And just look at the proof that I put on the lecture notes. See the new proof of the theorem in the lecture notes. Okay, so let's prove this bound here. Okay, proof. Actually, one should realize that this is really it's a statement that is global on a compact set, but it's only interesting for points that are close enough. What we should do, what we should prove is that if two points are close enough in the rho distance, then they are close enough uniformly in the d lambda distance. Now, more precisely, I'm claiming that it is enough to prove that there exists some interval, so neighborhood or compact neighborhood of lambda 0 in capital lambda, such that for all epsilon greater than 0, there exists some delta greater than 0, such that whenever you have points P and Q in K, and you have a rho distance between P and Q less than delta, and you get a parameter lambda in I, then this will imply that also the d lambda distance is small and is smaller than epsilon. Okay, so this epsilon does not depend on lambda and the points P, Q, the delta. Okay, in other words, what we need to prove? We need to prove that if you take the rho, respect to the rho distance, you take the delta ball at P, then this is contained in the d lambda distance, in the ball respect to the d lambda distance at center at P with radius epsilon. And this has to be for all P in K and for all lambda in I. So, and once you prove this, then you just fix, then you should imagine that the delta is just this. You define beta to be, I mean, or the inverse of beta is this delta. Now, but let's look at this inequality, right? So what we are saying is that, you know, if we fix epsilon, this ball, we know that if the structure is bracket generating, then this ball is really an open set, as an open neighborhood of P. So of course this will contain some delta ball, right? So you can think this to be Euclidean, some delta ball around P. What is important in this case is to find a control on delta that is independent on the distance, on lambda. So what one should think is that we are going to prove a a uniform version of Chau's theorem, Chow-Rachevsky's theorem. Okay, so more or less we need to revise the proof of the theorem. So let's define the following vector fields. xi lambda at P is the vector, tangent vector, f lambda P ei, where this ei, this is the ith element of the standard basis. Basis of Rm. So as a function of P, these are vector fields, and what we have assumed is that the vector field x1 lambda 0 up to xm lambda 0, they are bracket generating on the manifold. Now, as a consequence of the fact that these vector fields are smoothly depending on lambda, what we have is that on compact sets, on the compact set that we fix K, we have that also the vector fields x1 lambda, xm lambda, they are bracket generating. On K. And this is because if they're bracket generating at one point, P, by continuity, they stay bracket generating. So if you have iterated brackets that are linearly independent and they span the whole tangent space, then by continuity in lambda, the same thing is valid for a neighborhood of the point and a neighborhood of lambda 0. By compactness of K, we have that this is a whole is true for all lambda in some neighborhood, which we still call lambda in our proof of lambda 0. So, all right, so all these vector fields are bracket generating. Now, let's remember what was the proof of the orbit theorem or Chau's theorem. Right? So, Chow-Rachevsky will tell us that one can consider the map that to every t in some Rn associate the flow. So you start from an arbitrary point P, then you flow along a vector field x I1 for time t1, and then you keep flowing x in tn. This map has a regular point near 0, actually arbitrarily near 0. Now, where these are the vector fields chosen in some order. Now, what is the problem? The problem is that the order might depend on P. However, what we knew from this n was that it was enough to choose twice the dimension of M. And now, the way you can order M vectors or repeatedly enumerate M vectors with strings of length twice the dimension of M, this is a finite it's a finite string. So let's consider all possible enumerations. So now let's what we will do, we will choose all possible strings. The strings are called words. So let omega be a word in m letters that contains as subwords all possible words in m letters of length twice the dimension of m. And we are going to call n the length of this big word omega. Okay, and then what we'll have is that therefore for all p in K, for all P, the map where you choose now the word omega 1, omega n, has a regular point arbitrarily close to 0, to 0. However, the regular point might depend on P. This is possible, okay? Right. Okay, so, but now let's fix P and let's consider a regular point and therefore use the inverse mapping theorem. Okay, let's write down what we want to prove, at least initially. We want to prove this following claim, that for the moment, let's fix P and let's fix also some lambda. And also we fix an epsilon. We want to prove that there exists some delta and there exists some neighborhood of lambda inside the space of parameter capital lambda, such that the ball, respect to the Riemannian distance rho radius delta, is contained in the ball respect to the distance d lambda at P with radius epsilon. And this is for all lambda in this for all say lambda prime inside I. So initially we want to prove this, and then we will upgrade this by compactness to actually every possible lambda prime in capital lambda, and we will choose a delta that will not depend on P and lambda. Okay? So first we want to prove this. Okay. Now let's consider the map that we were considering before. Let's give a name. So let's call psi P lambda T to be the map, the composition of the flows in the order of this big word. So these are vector fields X lambda T1 at P. So we have this map, and since the vector fields are assumed now are bracket generating, then we know that there exists some t hat. So now fix P and lambda. Okay, so there exists T in the ball, Euclidean ball of radius epsilon in Rn, with the property that t hat is a regular point for the map psi P lambda with these entries. So t hat is a regular point for this map, and moreover, and this point goes to P, and it goes via this map to the point P. So this was Chow's theorem. Now, if you have that this point is a regular point for this map, since these maps depend smoothly on lambda, then what we can move lambda in a neighborhood and still have that this point is a regular point. So what we have is that there exists some I lambda, neighborhood of lambda, for which this point here, this t hat, is a regular point for psi p lambda prime dot for all lambda prime in I. Okay, very good. So now we want to apply the inverse mapping theorem. So what we will know is that the point P, the map, this map psi, will send a neighborhood of t hat onto some neighborhood of the image. Okay. Now, how big is this neighborhood will depend on two things. Will depend on the differential at t hat, like how much it squeezes like on the determinant of some minor of the minimum of the determinant of the differential, and on the second derivative of the map on the domain. So let me make this remark, which is important. So the inverse mapping theorem, or inverse function theorem, inverse function theorem implies that the map psi p lambda dot sends a neighborhood of t hat onto some neighborhood of the image, which in this case is P. And what I want to remark is that the size of these neighborhoods depend or can be controlled with a lower bound in terms of the differential at t hat and of the map at the regular point. So the differential at a regular point of the map and the second derivatives in some neighborhood. So this is a quantitative version of the inverse function theorem. Okay, we can discuss this on Teams, or I can make a video out of it if you want. Okay, so now we are going to use this quantitative version to all the maps where now psi the lambda varies to lambda 1, and but still we always have the same regular point. Okay, so by this quantitative inverse function theorem, now up to maybe restricting this neighborhood of lambda, we have that there exists some delta for which the ball at P, radius delta, is contained in the image P lambda prime T plus an epsilon neighborhood. And this is for all lambda prime in I lambda. Notice, okay, maybe in general one here should have put psi of P lambda prime T hat. No, it's T hat. But again, because of continuity, then for lambda close enough, this is close to P. Okay. Right. Okay. So here we have T hat. And okay, so we have this property. Now, remember that T hat was chosen to be inside the ball of radius epsilon. And therefore, here we have the containment phi P lambda prime, the ball of radius 2 epsilon. Good. Now, my claim is that this last set, so this I'm going to make a claim, I'm going to show that this contains it's contained in the ball with respect to the distance d lambda prime, centered at P, and radius some constant times epsilon. Okay, so I'm going to prove now this following claim. Okay, now what is this constant C? This constant is just going to be a bound on the norm, which we might vary in lambda, on the compact set we are considering. So, first of all, okay, one note first. The set psi with p varies in k and lambda in the whole space lambda and t in the whole, say, unit ball, closed unit ball. So all these are compact, these are continuous function, and therefore this map is this set is compact. Okay, being constant on this set, the function n, the norms, have a maximum. Okay, therefore there exists a constant c such that n p now will vary in this set here. Lambda will vary in capital lambda. V, this will be bounded by a constant V. And let's take the L1 norm. Okay, so this is true for all P in K, and for all actually for all P not in K but in psi K lambda V1, and for all small lambda in capital lambda, and then because it's linear, it's a norm, we have this part. Okay. Now, and see that this constant does not really depend on p or on epsilon, right? So this is something that we had since the beginning. Okay. So now I promise to check that this point, every element in here has distance at most c epsilon from p. So let's bound the distance of these points. So now we bound the distance, the lambda distance from P to phi lambda PT. Was it this the point? Let's see. P, okay, I'll call lambda prime. And then we have a point in the ball of radius 2 epsilon. Okay, now how can you bound this? Okay, we have a curve that reached this point, right? So this was, remember, this point was the flow of x lambda omega n Tn by definition. X omega 1 T1 at P. So this is a zigzag curve that starts from P. This is piecewise, so linear, or piecewise constant control. Okay, so which means that what we can take the control to be on some interval, say we parameterize from 0, 1. So on the first nth interval, we have constant control, which is exactly equal to this number times time tn. So what I'm claiming is that now we can take control so this distance here is bounded by the length of the curve that we are considering. It's a curve, okay, parameter lambda, this is gamma s control us in ds, where ut or us is the control that is okay, is a sum, okay, on the interval I minus 1 over n, I over n, I goes from 1 to n, is constantly equal to n times ti ei. Okay, so this is the control of that gives this curve or this final point. Good. So now we have the bound for the norm. So this is less than the integral of c times the norm of u. This was for the bound that we had on the norm. Okay. And now let me just do that. So this is constant, piecewise constant, and the calculation exactly gives c times the L1 norm of D1. Okay, so what we have, what we prove is that d lambda distance from P to phi P T lambda P T is less or equal than constant times norm of T. Okay, so what therefore we proved? We proved that that this claim is true, and therefore we have that this ball is inside this ball. Okay, so let me summarize what we have. So hence, for all p in k, for all lambda in lambda, there exists I lambda, neighborhood of lambda, such that the ball center at p, radius delta, for the raw distance is contained in the ball respect to the distance d lambda prime, center at p with radius epsilon for all lambda prime in I lambda. Okay. Now it's an easy it's an easy exercise using the fact that lambda is compact and k is compact to upgrade it to show that the delta might be chosen as so small, still positive, for which this is true for all p and lambda. So by compactness of k and lambda, one has what we wanted. For any epsilon, there exists delta such that the ball center p radius rho is contained in both the ball d lambda p epsilon for all p in k and for all lambda in lambda. Maybe I'll write this standard compactness argument in the lecture notes. And this is the end of the proof of the lemma, and therefore the end of the proof of the theorem. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.